Right now, as you sit here listening to these words, you are trapped. Not by walls, not by gravity, not by anything you can see or touch, but by something far more absolute. The boundary that holds humanity inside this solar system is not a distance. It is not an engineering problem waiting for the right rocket. It is a wall built from physics itself, and the closer you look at it, the more impossible it becomes to imagine ever crossing it. Scientists have run the numbers for decades. They have designed propulsion systems on paper, they have calculated fuel requirements, radiation doses, structural limits, and every single calculation arrives at the same terrifying conclusion. The universe was designed to keep biological life confined to its home star system. Not by accident, not by oversight, but as a direct consequence of how matter, energy, and time interact at the scales required for interstellar travel. By the end of tonight, you are going to understand exactly why crossing that boundary may be the one thing humanity will never accomplish, no matter how long we exist as a species. If you find these journeys into the deep mathematics of space as fascinating as I do, please take a moment to like the video and subscribe to the channel. It genuinely helps more than you know, and it lets me keep making these long-form explorations of what the cosmos really demands of anyone foolish enough to try crossing it. Now settle in, get comfortable, and let's begin. The story has to start with something most people never think about: the size of the box we live in. Not the planet, not the orbit of the moon, not even the orbit of Pluto, the actual gravitational territory of our sun, because when most people picture the solar system, they picture 8 planets in a row, and somewhere out past Neptune, a fuzzy edge where things just sort of stop. That image is not just incomplete. It is almost laughably small compared to the actual shape of our home in space. The sun's gravitational influence does not end at Neptune. It does not end at the Kuiper Belt. It does not even end at the heliopause where the solar wind finally surrenders to the interstellar medium. The sun holds objects in orbit out to a distance of roughly 100,000 astronomical units. That number deserves to sit in your mind for a moment. 100,000 times the distance from the Earth to the sun. Roughly 1.5 light years, nearly 40% of the way to the nearest star. Within that volume drifts the Oort cloud, a vast spherical shell of icy bodies that surrounds the entire planetary system. We have never directly seen a single Oort cloud object. We have only inferred their existence from the comets that occasionally fall inward from that frozen darkness. And there are trillions of them out there, scattered through a sphere so enormous that the entire region of the planets becomes a microscopic dot at its center. This is the territory you have to cross to leave the solar system. Not the few billion miles to Neptune, not the 12 billion miles where Voyager currently drifts. The full 1.5 light years to where the sun's gravity finally loses its grip, and another star's gravity begins to take over. And here is the first piece of the terror. Voyager 1, the fastest object ever to leave Earth on an outbound trajectory, has been traveling for nearly 50 years. It has covered roughly 15 billion miles. To reach the inner edge of the Oort cloud at its current speed, it will need another 300 years. To exit the outer edge into true interstellar space, free of the sun's gravity entirely, it will need approximately 30,000 years. Voyager will be a dead piece of metal long before it leaves the solar system. The plutonium powering its instruments is already failing. By the early 2030s, it will fall completely silent, and it will still be inside the sun's gravitational territory for roughly the next 30 millennia. This is humanity's fastest spacecraft. This is our best effort, and it is not even close to leaving the box. Now hold that image in your mind, because we have to add the next layer of the problem. The scale of the journey is only the surface. Underneath it lies something far more fundamental. The energy required to actually cross those distances within any meaningful time frame is governed by a single equation that humanity has been wrestling with since the dawn of rocketry. Konstantin Tsiolkovsky derived it in 1903. It is so simple it can be written on a napkin. And it is so cruel that physicists sometimes call it the tyranny of the rocket equation. The equation tells you how much fuel a rocket needs to reach a given velocity, and the answer scales exponentially, not linearly, not quadratically, exponentially. To double the velocity of your spacecraft, you do not need twice the fuel. You need vastly more than twice the fuel. Because all that extra fuel has mass, And all that mass has to be accelerated, which requires more fuel, which adds more mass, which requires more fuel, and so on in a feedback loop that climbs faster than any physical quantity can satisfy. For chemical rockets, the kind that have launched every human and every payload into space for the entire history of spaceflight, the maximum exhaust velocity is fundamentally limited by the chemistry of combustion. You can only make hydrogen and oxygen burn so efficiently. The energy released per kilogram of fuel has a hard ceiling set by the structure of chemical bonds themselves. No engineering breakthrough will ever raise that ceiling. The math is unforgiving. To accelerate a 1,000 kilogram probe to 1% of the speed of light using the most efficient chemical fuel ever conceived, you would need a starting fuel mass exceeding the total mass of the observable universe. This is not an exaggeration for dramatic effect. This is what the equation actually returns when you plug in real numbers. Every star, every planet, every galaxy, every atom of ordinary matter that exists, gathered together and burned as rocket fuel, would not provide enough thrust to push a small probe to a fraction that is still hopelessly slow for interstellar travel. 1% of light speed sounds fast, but at that velocity, the journey to Proxima Centauri would still require over 400 years. So chemical rockets are out. They cannot ever be the answer. They are not slightly inadequate. They are not almost good enough. They are mathematically impossible for the task. This realization alone should be sobering. The rockets that took humans to the moon, the rockets that launched every space telescope, every interplanetary probe, every satellite humming overhead right now, these rockets are not stepping stones to the stars. They are the absolute pinnacle of what one branch of propulsion physics can ever achieve, and that pinnacle is not even within shouting distance of what interstellar travel demands. Engineers and physicists have known this for decades. They have proposed alternatives. Each alternative comes with its own terrifying compromise. Nuclear pulse propulsion was the first serious contender. The idea was conceived in the late 1950s under the codename Project Orion, and it remains one of the strangest ideas ever taken seriously by mainstream science. The concept was straightforward in the way that only mid-century engineers could make a horrifying idea sound straightforward. You build a spacecraft with a massive steel pusher plate at the rear. You eject nuclear bombs out the back, one at a time, on timed intervals. You detonate each bomb at a precise distance from the plate. The expanding plasma fireball slams against the plate, transferring momentum to the spacecraft, and you ride this cascade of nuclear explosions to velocities that no chemical rocket could ever approach. The team behind Orion included Freeman Dyson, one of the most respected theoretical physicists of the 20th century. They were not science fiction writers. They were running real calculations, building real test models, conducting real experiments with conventional explosives. The physics worked. The engineering, terrifying as it sounded, was within reach. Calculations showed that an Orion spacecraft could potentially achieve 8 to 10% of the speed of light using fusion bombs in a more advanced design. At that velocity, the trip to the nearest star would still require over 40 years from the perspective of an outside observer, but it was within the realm of possibility. It would have worked. The 1963 Partial Test Ban Treaty effectively ended the program. Detonating thousands of nuclear weapons in space, even in the name of exploration, was not something the international community was willing to allow. And so, the most realistic near-term path to interstellar velocities was shelved, possibly forever. But even if Orion had been built, even if it had launched, it carried its own brand of terror. The crew would ride atop a continuous string of nuclear explosions for years. The radiation environment alone would be catastrophic without massive shielding, which would in turn add mass that the equation could not afford. And the spacecraft would be carrying enough nuclear weapons to end most planetary civilizations. A failure during launch from Earth would have rained radioactive debris across continents. A failure mid-flight would have ended every life aboard in microseconds. Nuclear thermal rockets offer a tamer alternative. They work by passing hydrogen propellant through a nuclear reactor, heating it to extreme temperatures, and expelling it through a nozzle. NASA tested these engines extensively under the NERVA program in the 1960s. They work. The technology is mature. The problem is that nuclear thermal rockets only roughly double the performance of chemical rockets. They get you to maybe 100,000 miles per hour. At that speed, the journey to Proxima Centauri requires approximately 28,000 years. Better than chemical rockets, but still longer than the entirety of recorded human civilization. Whatever crew you sent would die long before reaching their destination, along with their children, their grandchildren, and roughly 900 more generations after that. Then there is fusion, the dream of every propulsion physicist. Combining light atomic nuclei to release energy, the same process that powers the sun. In principle, a fusion rocket could achieve exhaust velocities of 3 to 5% of the speed of light, allowing spacecraft to reach 10 to 15% of light speed with reasonable fuel ratios. The British Interplanetary Society spent years on a detailed design called Project Daedalus in the 1970s. It was a two-stage spacecraft, 54,000 tons at launch, almost all of which was fuel. It was designed to reach Barnard's star in 50 years at 12% of light speed. It would carry no deceleration system. It would simply screen through its target system at thousands of kilometers per second, conducting observations in the few days it spent within range, and then continue forever into the void beyond, unable to stop or turn around. And here is the catch that breaks the dream. We have been working on controlled fusion for over 70 years. Every laboratory in the world combined still cannot produce a fusion reactor that generates more energy than it consumes. The conditions required for sustained fusion, temperatures of hundreds of millions of degrees, pressures that compress hydrogen plasma into densities that have no natural analog, are achievable only in the cores of stars or in the brief instant of a hydrogen bomb detonation. Reproducing those conditions in a controlled, reliable, compact form that can sit inside a spacecraft engine is a problem we have not solved, and the optimistic estimates for when we might solve it stretch decades into the future. Even then, there is a vast gap between achieving net positive fusion in a stationary reactor and building a fusion engine compact enough to fit inside a spacecraft, light enough to be accelerated, and reliable enough to operate continuously for the years required to reach interstellar velocities. Antimatter is the next step up the propulsion ladder, the most energy-dense fuel that physics permits. When matter encounters antimatter, both annihilate completely, converting 100% of their combined mass directly into energy. A single gram of antimatter annihilating with a gram of normal matter releases roughly 180 trillion joules of energy. That is the explosive yield of the Hiroshima bomb concentrated in 2 grams of material. With antimatter, the rocket equation finally becomes survivable. The exhaust velocity approaches a significant fraction of light speed. Spacecraft accelerations to 70 or 80% of light speed become mathematically plausible. The journey times shrink dramatically when you factor in time dilation. A traveler could reach nearby stars in subjective years rather than centuries. But antimatter does not exist naturally on Earth, or anywhere else for that matter in any quantity worth mentioning. The total amount of antimatter ever produced in human history, gathered together from particle accelerators across decades of research, would not be enough to power a household light bulb for more than a few seconds. Producing antimatter is the most energetically wasteful process humans have ever attempted. To create 1 gram of antimatter through current methods would require roughly 10 billion times more energy than the antimatter ultimately stores. Producing enough antimatter for a single interstellar mission, perhaps a few kilograms at most, would consume the total electrical output of human civilization for centuries. That energy has to come from somewhere. We would need to harvest it from the sun, build solar collection arrays the size of small planets, dedicate the next 100 generations of human technological output to manufacturing fuel for 1 mission. And that is just to make the antimatter. Storing it is its own nightmare. Antimatter annihilates instantly upon contact with normal matter, which means it cannot touch anything. Not the walls of its container, not stray molecules of gas, not a single atom of contamination. It must be suspended in perfect vacuum using magnetic fields, held in place by precisely calibrated electromagnetic forces for the entire duration of storage. The longest anyone has ever successfully stored antimatter is approximately 16 hours, achieved at CERN in 2023. To reach a nearby star, you would need to store antimatter reliably for decades, an improvement factor of roughly 10,000 over current best results. And if anything goes wrong, even for a fraction of a second, even because of a tiny power fluctuation or a vibration during launch, your fuel supply does not just leak away. It explodes with the force of a nuclear weapon. Your spacecraft becomes a fireball visible across light years. So that is the situation with onboard propulsion. Every option falls into one of two categories. Either it works on paper but cannot generate enough velocity, or it generates enough velocity but cannot be built with anything resembling current or foreseeable technology. There are also the so-called beamed propulsion concepts, which try to escape the rocket equation entirely by leaving the energy source at home. Project Breakthrough Starshot, announced in 2016 with funding from Russian billionaire Yuri Milner and the endorsement of the late Stephen Hawking, is the most serious modern proposal. The idea is to build a ground-based laser array with combined power output approaching 100 gigawatts, equivalent to 100 large nuclear power plants running simultaneously. The laser would focus on a tiny spacecraft, just a few grams in mass, attached to a lightweight reflective sail measuring a few meters across. The intense photon pressure would accelerate this gossamer probe from rest to 20% of the speed of light in about 10 minutes. At that velocity, the probe could reach Alpha Centauri in roughly 20 years. This sounds like the answer, until you start examining the details. The laser array has to maintain coherent focus on a target accelerating away from Earth at thousands of kilometers per second. Any misalignment, even by a microscopic angle, sends the beam past the sail entirely. The sail itself has to survive radiation intensities that would vaporize any conventional material. The materials science needed to build such a sail does not yet exist, only theoretical concepts that might work in principle. The probe is so small that it cannot carry meaningful instrumentation, only a handful of cameras and a tiny transmitter. And here is the real problem. Once you have accelerated to 20% of light speed using the laser, there is no way to slow down. There is no laser at the destination pushing back against you. The probe would scream through the Alpha Centauri system in a matter of hours, snapping a few photographs, attempting to transmit them across 4 light-years using a transmitter weaker than a child's flashlight, and then continuing forever into the void beyond. For a robotic flyby that might return a handful of grainy images, this approach offers some hope. For sending humans to actually arrive at another star, to stop, to explore, to live, this approach fails completely. Beamed propulsion is a one-way ticket past the destination, not to it. Now we come to the second wall, the one that a lot of people never even consider because they are still focused on the first wall, the problem of generating enough velocity. But suppose for a moment that you have solved propulsion entirely. Suppose someone has cracked controlled fusion, or developed a way to manufacture antimatter at industrial scales, or invented some new physics that lets a spacecraft reach a substantial fraction of light speed. Even in that universe, the second wall is still waiting. And it is arguably worse than the first. Space is not empty. This is one of the most persistent misconceptions about the cosmos. People imagine the void between stars as a perfect vacuum, a pristine emptiness through which a spacecraft could travel without resistance. The reality is that interstellar space contains, on average, about 1 hydrogen atom per cc. Sometimes more, sometimes less, depending on the local density of the interstellar medium. There are also dust grains, tiny specks of carbon and silicate material left over from dying stars, scattered through the void at far lower densities but never absent entirely. At normal velocities, none of this matters. Voyager passes through this thin haze without noticing, because at 38,000 miles per hour, a hydrogen atom hitting the spacecraft delivers an utterly negligible amount of energy. The interstellar medium might as well not exist from Voyager's point of view, but energy of impact scales with the square of velocity. Double your speed, and the kinetic energy of every collision quadruples. Multiply your speed by 10, and the energy of each collision becomes 100 times greater. By the time you reach 10% of the speed of light, every hydrogen atom encountered carries the energy of a high-energy cosmic ray particle. By the time you reach 50% of light speed, each collision is depositing energies equivalent to particles produced in our most powerful particle accelerators. At 90% of light speed, every grain of interstellar dust, every atom of hydrogen, every molecule of methane drifting in the void becomes a projectile, carrying the energy of a small artillery shell. Consider what this actually means for a spacecraft. A vessel with a 1 square meter cross-section traveling at 10% of the speed of light through the typical interstellar medium will encounter approximately 100 trillion hydrogen atoms every second. Each collision delivers a tiny amount of energy individually, but they add up to thousands of watts of continuous power deposition into the forward surfaces of the ship, not as gentle warmth, as a constant sleet of ionizing radiation, knocking atoms out of position in the hull material, breaking molecular bonds, creating cascades of secondary particles that penetrate deep into whatever lies behind the outer skin. Over years of travel, this exposure accumulates, materials become brittle, electronics develop random faults. Biological tissue, if any is aboard, accumulates lethal radiation doses long before reaching the destination. Then come the dust grains. Larger than atoms, far less common, but vastly more dangerous when encountered. A single grain of dust, perhaps a milligram in mass, hitting a spacecraft at 10% of light speed, delivers kinetic energy comparable to a stick of dynamite. A pebble, just a few grams, would impact with the force of a small nuclear weapon. The math is not subtle. Kinetic energy is 1/2 mass times velocity squared, and at relativistic speeds, the velocity squared term grows without limit. There are no fender benders at these velocities. Every collision is catastrophic. Engineers have proposed solutions. Massive shielding at the front of the spacecraft. Layers of ablative material designed to vaporize on impact and disperse the energy. Magnetic deflection fields that could push aside charged particles before they reach the hull. Active scanning systems that could detect incoming dust grains and either evaporate them with lasers or maneuver around them. Each proposal sounds plausible in concept. Each runs into the same fundamental problem when you examine the engineering. Shielding adds mass. Mass that has to be accelerated to relativistic velocities along with the rest of the spacecraft. Mass that pushes the rocket equation back into impossibility. Magnetic fields require power, often immense power, generated continuously for the entire duration of the journey. Active scanning requires reaction times measured in microseconds, because at 10% of light speed, your spacecraft is covering 30,000 kilometers every second. By the time a grain of dust is detected, you have less than a millisecond to evade it. No human reflex can respond at those speeds. Every defensive system must be fully autonomous, running on artificial intelligence that has to function flawlessly for decades, without human intervention. Even if you solve all of that, there is still the question of larger objects. The interstellar medium contains not just gas and dust, but occasional larger bodies. Rogue planets ejected from their original star systems, drifting through the void with nothing to mark their passage. Comets and asteroids that have escaped their parent systems entirely. We do not know how many such objects exist, because they are too dark and too far apart to detect with current telescopes. They could be vanishingly rare, or they could be surprisingly common. Statistically, the chance of a single spacecraft encountering one along a 4-light-year journey is small. But it is not zero, and if your trajectory happens to intersect such an object at relativistic velocity, no amount of shielding will save you. The spacecraft and everything it carries simply ceases to exist. Whatever was on board becomes plasma. And the journey ends in an instant that no one back on Earth will know about for years afterward. When the expected signals fail to arrive and the silence finally becomes undeniable. This is what the second wall actually looks like. Even if you solve propulsion, even if you generate enough velocity to make interstellar travel feasible in principle, you have created a vessel that is now flying through a sleet of relativistic radiation, dodging objects it cannot detect in time, with every system held together by engineering tolerances tighter than anything humans have ever built. And it has to do this for years, decades, possibly longer, depending on the destination. Every component, every weld, every line of code must work continuously throughout that span. There is no maintenance crew. There is no resupply. There is no rescue. If anything fails, even one critical system, the mission ends. But the second wall has another layer that we have not yet touched. Because if your spacecraft is carrying living things, the radiation environment is not just damaging your hull, it is destroying your crew. Galactic cosmic rays are perhaps the most underappreciated threat in all of space exploration. Most people, when they think about radiation in space, picture solar flares, the dramatic outbursts from the sun that can damage satellites and threaten astronauts. Solar radiation is dangerous, but it is also predictable. The sun has cycles. We can monitor it. We can shelter from it. We can build storm shelters into spacecraft and time our missions around solar minimums. Galactic cosmic rays are a different beast entirely. They come from outside the solar system, from supernova explosions, from active galactic nuclei, from violent events scattered across the entire Milky Way and beyond. They arrive at Earth from every direction, all the time, with no schedule and no warning, and they carry energies that dwarf anything our sun produces. Within the solar system, the heliosphere provides partial shielding. The sun's magnetic field, carried outward by the solar wind, deflects a significant fraction of incoming cosmic rays. Earth's own magnetic field provides additional protection for everything orbiting close to the planet. Astronauts on the International Space Station receive elevated radiation doses, but the bulk of the cosmic ray flux is absorbed or deflected before it ever reaches them. Step outside the heliosphere into true interstellar space, and that protection vanishes. The cosmic ray flux roughly doubles. And for any mission lasting decades, the cumulative dose becomes catastrophic. NASA has studied this problem extensively. Their models suggest that an unprotected human body in deep space would accumulate a lethal radiation dose within roughly 2 to 3 years. Even with significant shielding, the long-term cancer risk for crew members on a multi-decade interstellar mission becomes nearly certain rather than probabilistic. Beyond cancer, there are subtler effects. Cosmic ray particles can damage neurons in the brain, causing what researchers call cognitive degradation. Studies on mice exposed to simulated cosmic radiation show measurable losses of memory function, problem-solving ability, and emotional regulation. The effects are not reversible. Whatever damage is done is permanent. A crew exposed to deep space radiation for the duration of an interstellar mission would likely arrive at their destination, if they arrived at all, with significantly diminished cognitive faculties. The astronauts who launched as brilliant scientists and engineers might emerge as confused and forgetful shells of themselves, no longer capable of the precise work the mission requires. The shielding solution is theoretically possible, but practically devastating. To reduce cosmic ray exposure to manageable levels, you would need shielding equivalent to roughly 2 meters of water surrounding every habitable area of the spacecraft. 2 meters of water around a habitat large enough to support a crew for decades represents an enormous mass. And mass, as we have established, is the enemy of any spacecraft trying to reach relativistic velocities. Every kilogram of shielding is a kilogram that has to be accelerated. A kilogram that demands more fuel. A kilogram that pushes the rocket equation deeper into impossibility. There are alternatives. Magnetic shielding could in principle deflect charged particles around the spacecraft, much as Earth's magnetosphere protects the planet's surface. But generating magnetic fields strong enough to deflect high-energy cosmic rays requires superconducting coils carrying enormous currents, surrounded by their own structural support, all of which adds mass and complexity. And not all cosmic rays are charged. Some fraction are neutral particles that magnetic fields cannot deflect at all. These would pass through any magnetic shield and continue into the spacecraft, depositing their energy in whatever they encountered. Now layer this on top of the relativistic dust problem we discussed earlier, and the picture becomes even bleaker. Your forward shielding is being eroded continuously by impacts with interstellar atoms and dust grains. Your crew is being slowly poisoned by cosmic rays passing through whatever shielding the rocket equation allows. Your electronics are accumulating radiation damage that increases the probability of failure with every passing year, and every fix to one of these problems makes the others worse. Add more forward shielding to handle dust, and you have to add more cosmic ray shielding around the crew, and you have to add more fuel to accelerate all that mass, and you have to add more structural support to handle the larger fuel tanks, and the spacecraft balloons in mass until the propulsion system cannot move it at all. But suppose, somehow, you have solved all of this. Suppose your fictional civilization has cracked propulsion physics and developed shielding light enough to be carried but effective enough to protect the crew. You have crossed the first wall and the second wall. Now the third wall rises in front of you. And this one cannot be solved by any technology, because it is not a technological problem, it is a problem of time itself. Here is what no propulsion advance can ever change. The speed of light is the absolute speed limit of the universe. Nothing with mass can ever reach it, let alone exceed it. This is not an engineering challenge. This is a fundamental property of spacetime, woven into the equations Einstein derived over a century ago and confirmed by every experiment conducted since. As an object accelerates, its kinetic energy grows. At low velocities, this growth is gentle. Double your speed, quadruple your kinetic energy. But as you approach light speed, the energy required to accelerate further begins climbing faster than predicted by ordinary physics. The object behaves as though it has more mass than it started with. This is relativistic mass increase, and it grows without limit as velocity approaches light speed. To reach light speed itself would require infinite energy. And since infinite energy does not exist anywhere in the universe, light speed remains forever out of reach for anything carrying mass. This means that even with perfect propulsion technology, even with unlimited fuel and flawless engineering, your maximum velocity is capped. You can get arbitrarily close to light speed, adding more nines after the decimal point, but you can never quite arrive. And every additional 9 costs exponentially more energy than the previous one. The closer you push toward light speed, the more brutally the laws of physics resist you. There is a real, physical, unbreakable ceiling on how fast any spacecraft can travel between the stars. Now combine this ceiling with the actual distances involved. Proxima Centauri is 4.2 light-years away. That distance is defined by the time light takes to cross it. If you traveled at exactly the speed of light, which you cannot, the journey would take 4.2 years from the perspective of an observer back on Earth. Any traveler aboard a real spacecraft, moving at less than light speed, will take longer. How much longer depends on what fraction of light speed they achieve. At 10% of light speed, the trip takes 42 years. At 50%, it takes 8.4 years. At 90%, 4.7 years. At 99%, 4.25 years, just barely longer than the absolute minimum. The minimum journey time to the nearest star is therefore something like 4 years, and that is for the closest possible destination. The next nearest stars are 6 light-years away, then 7, then 8. Most stars worth visiting, those with confirmed planets, those of similar age and stability to our Sun, are tens or hundreds of light-years distant. The TRAPPIST-1 system, with its 7 Earth-sized planets, lies 40 light-years away. The Kepler-186 system, with its potentially habitable planet, sits roughly 500 light-years from us. To reach these destinations, even at velocities close to light speed, requires journeys measured in centuries from Earth's perspective. This is where time dilation enters the picture. Einstein's special relativity tells us that as an object approaches light speed, time aboard that object slows down relative to a stationary observer. A traveler moving at 99% of light speed experiences approximately 1 year of time for every 7 years that pass on Earth. At 99.9%, the ratio jumps to roughly 1 to 22. At 99.99%, 1 to 70. At 99.999%, 1 to over 200. Time dilation provides what looks like a loophole. The traveler can age slowly, while the universe outside ages quickly. A journey of 40 light-years can be experienced as just a few years aboard the spacecraft, if the spacecraft is moving fast enough. But the loophole comes with a catch that turns out to be the third wall. Time dilation does not bring you closer to home. It only takes you further away. A traveler who departs Earth at 99.9% of light speed for a journey to a destination 40 light-years away will experience perhaps 2 years of subjective time during the trip. They will arrive having aged minimally, but Earth will have aged 40 years. The civilization that launched them will have moved on without them. Their families will be elderly or deceased. Their colleagues will have retired. The technology they trained on will be obsolete. The cultural references they grew up with will be ancient history. They will be strangers in time, separated from their original world by a gulf that no spacecraft can cross. If they choose to return, the situation becomes even more extreme. A round trip to a destination 40 light-years away at 99.9% of light speed will take roughly 4 years of subjective time for the traveler. But Earth will have aged 80 years during their absence. They will return to a planet they no longer recognize, in a future they did not choose, separated permanently from everyone and everything they ever knew. This is not science fiction. This is what the equations of physics actually require. Time dilation makes interstellar travel possible only by demanding that the traveler accept permanent exile from their own era. Push to higher fractions of light speed, and the problem grows worse. A round trip to the center of the Milky Way at extreme relativistic velocities might take a traveler 60 years of subjective time. They would return to find that 100,000 years had passed on Earth. The species that launched them might no longer exist. The planet itself might be unrecognizable. They would be a fossil, a living artifact from a vanished civilization, dropped into a future they have no preparation for. There is no way back. There is no return ticket. Once you accelerate to relativistic velocities and travel to another star, you have permanently left the era that produced you. The connection is severed. The bridge is burned. You can never go home, because home no longer exists in any form you would recognize. This is the third wall, the temporal isolation of relativistic travel. It is built into the geometry of spacetime itself. No amount of engineering, no propulsion breakthrough, no clever workaround can defeat it. The faster you travel, the more time passes on Earth while you are gone. The further you go, the more profound the disconnection. And there is no exception, no loophole, no special case where the rule does not apply. The mathematics is exact and merciless. Some have proposed faster-than-light travel as a solution. The Alcubierre drive, the wormhole, the warp bubble. These are ideas that occasionally appear in serious physics journals, dressed up in equations that suggest they might be possible in principle. But every one of these proposals requires something called negative energy density, a property of matter that does not exist in any quantity worth mentioning anywhere in the known universe. The most optimistic calculations for an Alcubierre drive suggest the energy requirements exceed the mass energy of the planet Jupiter, all in the form of exotic matter that may not be physically realizable. More realistic estimates place the requirements beyond the total mass energy of the entire observable universe. These are not engineering challenges to be solved with effort and time. These are mathematical curiosities that emerge from the equations of general relativity, but cannot be physically constructed because the necessary materials do not exist. Wormholes have similar problems. The mathematics permits them. Two distant points in space could in principle be connected by a tunnel through higher dimensional space-time, allowing travel between them at effectively faster-than-light speeds without violating special relativity. But stable, traversable wormholes require exotic matter to hold them open against gravitational collapse. Whether that exotic matter can exist in any meaningful quantity remains one of the great unanswered questions of theoretical physics. Even if it could, transporting the wormhole mouths to useful destinations would require solving the propulsion problem we have been discussing. One mouth would have to travel to Proxima Centauri at conventional velocities before establishing a shortcut back to Earth. The initial journey still requires solving every problem that wormholes were supposed to circumvent. So we are left with the equations as they actually are, and the universe as it actually exists, and the conclusion that any interstellar journey must respect the speed limit of light, which means accepting either centuries-long voyages or permanent temporal exile from the home era. Every option carries a price that is essentially infinite. There is no version of this problem where humanity sends explorers to the stars and gets them back into the same world they left. The act of leaving is irreversible. The act of returning, if it happens at all, is a return to a future that has nothing to do with the past you carried with you. But all of this assumes the spacecraft makes it, that the propulsion works, that the shielding holds, that the crew survives, that the systems function for the entire duration. Now we have to talk about the fourth wall, which is perhaps the most insidious of all. Because everything we have discussed so far has been about physics and engineering. The fourth wall is about biology. And biology, it turns out, has its own ideas about whether humans can ever cross interstellar distances. Humans evolved on a planet. We are tuned to its gravity, its atmosphere, its day-night cycle, its biosphere, its electromagnetic environment. Every cell in your body, every molecule of your DNA, every neural pathway in your brain has been shaped over hundreds of millions of years by the specific conditions of Earth's surface. Take a human being out of that environment, even just into low Earth orbit, and the body begins to fail. It happens slowly at first. Bones lose density at rates of 1 to 2% per month. Muscles atrophy without gravity to work against. The cardiovascular system reorganizes itself to handle the absence of blood pooling in the legs. Vision deteriorates as fluid pressure shifts inside the skull, deforming the back of the eyeball. The immune system weakens. Sleep cycles disrupt. Hormone production goes haywire. The International Space Station hosts crew members for missions typically lasting 6 months. Even after such relatively short durations, returning astronauts require months of physical therapy to regain the ability to walk normally. Some never fully recover. Long-term effects include increased cancer risk, accelerated aging, and persistent vision problems. And these astronauts are inside Earth's magnetosphere the entire time, partially protected from cosmic radiation. They are receiving regular resupply missions, fresh food, communication with Earth, the psychological support of knowing they can return home in an emergency. They are working in conditions that, by interstellar travel standards, are luxurious. Now imagine a crew on a spacecraft traveling to another star. The journey lasts decades or centuries, depending on velocity. There is no resupply, there is no return option. There is no rescue. The crew must remain healthy enough to function for the entire duration. They must reproduce, because the original crew will die long before the journey ends. They must educate their children to maintain the spacecraft they have never seen built. They must preserve their genetic diversity in a closed population that will inbreed catastrophically without careful management. They must survive psychologically in conditions of confinement that no human society has ever imagined. The closest analogs we have are submarine crews and Antarctic researchers. These groups spend months at a time in confined, isolated environments. Even those relatively short stays produce predictable patterns of psychological stress. Conflicts erupt over trivial matters. Depression and anxiety become widespread. Cognitive performance declines. Interpersonal relationships fracture. People who entered as friends emerge as enemies. People who started healthy emerge with chronic mental health conditions. And these are stays of months, conducted by carefully selected volunteers, with the knowledge that the assignment will end and they will return to normal life. Multiply the duration by decades. Remove the possibility of return. Add the knowledge that no one will ever come to help if things go wrong. The psychological pressure becomes something no human has ever endured. There are proposals to solve this through artificial means. Cryogenic suspension, freezing the crew for the duration of the journey and reviving them at the destination. The technology does not exist. We can preserve cells and tissues at low temperatures, but we cannot reliably revive a complex organism from such a state. The damage caused by ice crystal formation during freezing destroys cellular structures throughout the body. Various cryoprotective chemicals can reduce this damage, but none have allowed a mammal larger than a small lab animal to survive freezing and revival. Decades of research have not solved this problem, and there is no clear path to solving it in the foreseeable future. Generation ships avoid the cryogenic problem by accepting that the original crew will not survive the journey. Instead, they plan for a population to live, reproduce, and die aboard the spacecraft, with descendants completing the mission their ancestors began. This solution has its own problems. Maintaining a stable, healthy, technologically capable population in a closed environment for centuries is something humanity has never accomplished and may not be able to accomplish. The minimum viable population for genetic stability is somewhere between 500 and several thousand individuals, depending on how aggressively you manage breeding. Each of those people requires food, water, air, living space, medical care, and psychological support, all manufactured aboard the spacecraft from whatever raw materials it carries. The mass and complexity of a true generation ship is staggering. Estimates suggest such a vessel would have to be the size of a small city, carrying enough biological infrastructure to sustain its population indefinitely. And even if you build it, you have to ask whether the descendants who arrive at the destination still represent the civilization that launched them. After 10 generations, perhaps 300 years aboard a closed system, the population will have diverged culturally, linguistically, and possibly biologically from the population that departed Earth. They will be a new species in some meaningful sense. Adapted to spacecraft environments rather than planetary ones, They may have no interest in colonizing the destination world. They may consider the spacecraft itself to be home and the planet they were sent to a strange and inhospitable foreign land. The original mission may have been preserved in the historical records, but the actual humans who carry it forward may have evolved into something that no longer cares about the goals of distant ancestors. There is also the question of whether children born aboard such a vessel could even survive the transition to a planetary surface. Without normal gravity, their bones, muscles, and cardiovascular systems would develop differently from those of Earth-evolved humans. They might be physically incapable of standing upright on a world with Earth-normal gravity. Their immune systems, never exposed to the microbial diversity of a planet, would be wildly maladapted to any biosphere they encountered. The first human born in interstellar space might be the last human capable of crossing it, simply because their descendants would be too different from terrestrial humans to function as the colonists the mission was designed to deliver. This is the fourth wall. The biological constraint. Humans are not designed for interstellar travel. We are designed for one specific planet, in one specific gravitational environment, with one specific biosphere supporting our metabolism. Removing us from that environment, even for short periods, causes measurable damage. Removing us for the duration of an interstellar journey is something the human body has no evolutionary preparation for. We may simply not be capable of surviving the trip at all, regardless of the engineering of the vessel. Our bodies might give out long before the destination is reached. And the bodies of any descendants born along the way might be so different from our own that they no longer count as the same species. You might think this is where the list of walls ends. You would be wrong. There is a fifth wall, and in some ways it is the most disturbing of all, because it suggests that even successful interstellar missions might never tell us they succeeded. Even if everything works, even if a spacecraft launches and survives the journey and arrives at another star, even if the crew remains healthy and the technology remains functional and the destination turns out to be habitable, there may be no way to confirm any of this from Earth. The fifth wall is the wall of communication. Light speed is the fastest possible transmission speed for any signal. This applies to radio waves, lasers, and every other form of electromagnetic radiation. A spacecraft at Proxima Centauri sending a signal back to Earth requires 4.2 years for that signal to arrive. A signal sent from Earth to that spacecraft requires the same 4.2 years to reach it. A round-trip exchange of messages takes over 8 years. For any star further away, the delays grow proportionally. A spacecraft at the distance of the TRAPPIST-1 system would have a round-trip communication delay of 80 years. By the time you receive an answer to a question, the people who originally heard your question have likely retired or died. The conversation has been preserved in writing, in archives and historical records, but it is no longer a conversation in any meaningful sense. It is the exchange of letters across generations. This affects mission planning in profound ways. There is no real-time guidance from Earth. No troubleshooting help from mission control. No scientific consultation when the crew encounters something unexpected. Every decision aboard the spacecraft must be made autonomously, based on whatever information and expertise the crew carries with them. If something breaks, they have to fix it themselves, with no possibility of receiving help in time. If a medical emergency arises, the doctor on board must handle it alone, without the ability to consult specialists back home. If the mission encounters a situation no one anticipated, there is no procedure to follow except whatever the crew can devise on the spot. Communication itself becomes a question of whether anyone is still listening. A signal sent from a distant star reaches Earth over years or decades. During that time, the receiving infrastructure on Earth has to remain operational. The radio telescopes have to continue tracking the right region of sky. The institutional knowledge of the mission has to be preserved across multiple generations of researchers and administrators. The funding has to continue for the duration. Any breakdown in this chain of continuity, any war, any economic collapse, any change in scientific priorities, can result in signals arriving at Earth with no one to receive them. The mission could succeed brilliantly, send back priceless data and have its data lost simply because Earth stopped listening. There is also the inverse problem. The spacecraft has to remain in contact with Earth. Its communication systems have to function for decades, broadcasting back across light years with whatever power the dwindling onboard energy supply can provide. The signals weaken with the square of distance. By the time they reach Earth, they are extraordinarily faint, requiring enormous receiving antennas to detect it all. As the spacecraft ages, as components fail, as power degrades, the ability to transmit gradually weakens. There may come a moment when the spacecraft is still functional, still completing its mission, still gathering useful data, but no longer capable of transmitting that data back across the Gulf to Earth. The mission becomes a sealed time capsule, full of discoveries that no one will ever see. And then there is the deepest cut, the possibility that the spacecraft arrives, the crew thrives, the colony succeeds, and Earth never knows. Civilization continues in two locations, separated by light years of empty space, each carrying on with their own concerns, their own discoveries, their own history. They might exchange occasional signals across the void, but those signals are years out of date by the time they arrive. The two branches of humanity are effectively separate species in a temporal sense, never able to truly share an experience, never able to coordinate in real time, forever isolated by the simple fact that the universe has a maximum communication speed. This is what makes interstellar exploration fundamentally different from any exploration humanity has ever undertaken. The voyages of discovery that mapped Earth's continents, the missions that crossed the solar system to study other planets, all of these maintained connection between travelers and their home. Letters could be exchanged, data could be transmitted. The traveler returned, eventually, to share what they had found. Interstellar travel breaks this pattern absolutely. The traveler never returns. The home never learns, in any timely way, what the traveler discovered. The two sides of the journey become permanently separated by both space and time, connected only by signals so delayed that they function more like archaeology than communication. Now stack the walls together. The propulsion problem that may never be solvable, the radiation problem that destroys any crew foolish enough to attempt the crossing, the temporal isolation built into relativistic physics, the biological constraints that make humans poorly suited for the trip, the communication delays that sever any meaningful connection between the spacecraft and Earth. Each wall by itself is daunting. Together, they form a barrier that begins to look less like a series of engineering challenges and more like a fundamental property of the universe itself. As though the cosmos has been arranged specifically to ensure that biological civilizations remain confined to their home star systems, observing the rest of the galaxy from a distance, unable to ever truly visit. Some scientists have begun to wonder whether this confinement might be the answer to a question that has puzzled astronomers for over half a century. The Fermi paradox. The strange silence of a galaxy that should, by all probabilistic reasoning, be teeming with intelligent civilizations. There are hundreds of billions of stars in the Milky Way, many host planets. A significant fraction of those planets occupy habitable zones where liquid water could exist. Even if intelligent life is rare, it should have arisen many times across the history of the galaxy. Some of those civilizations should have arisen long before us, perhaps billions of years before us. They should have had ample time to spread across the galaxy, to colonize other star systems, to leave traces detectable by our telescopes. And yet, when we listen, we hear nothing. When we look, we see nothing. The galaxy appears empty, as far as our instruments can tell. The walls we have been discussing offer one possible explanation. Perhaps every civilization that arises encounters these same barriers. Perhaps every intelligent species, no matter how technologically advanced, hits the same combination of impossible physics and unforgiving biology. Perhaps the silence we hear is not the silence of an empty galaxy, but the silence of countless trapped civilizations, each one confined to its home star system, each one looking outward and concluding, just as we are concluding, that the stars are not actually accessible. The galaxy may be full of life. It may be full of intelligence. But every civilization is locked behind the same walls we are facing, and none of them has ever managed to break through. This idea has a name in the literature of speculative astrophysics: the Great Filter. It is the hypothesis that somewhere along the path from inert matter to galaxy-spanning civilization, there is an obstacle so severe that almost nothing gets past it. The filter could be located at any stage of the process. Perhaps the formation of life itself is extraordinarily rare, requiring conditions that seldom occur. Perhaps the leap from single-celled life to complex multicellular organisms is the bottleneck. Perhaps the development of intelligence is the rare step. Or perhaps, and this is the version that should worry anyone thinking seriously about interstellar travel, The filter lies ahead of us. Perhaps the obstacle is not in our past, but in our future. Perhaps every civilization that reaches our level of technological sophistication runs into exactly the walls we have been mapping. Perhaps interstellar travel is the filter. Perhaps the universe permits intelligent life to arise repeatedly, but does not permit it to spread. If that is true, the implications are sobering. It would mean that the silence of the galaxy is not evidence that we are alone, but evidence that we are trapped. It would mean that countless civilizations have come and gone over the billions of years the Milky Way has existed, each one rising on its home world, developing science, looking outward at the stars, dreaming of crossing the gulf, and ultimately failing. Not failing because they were not clever enough. Not failing because they did not try hard enough. Failing because the universe itself is structured to prevent the crossing. Each civilization eventually accepts the boundary, turns inward, and either fades into history without leaving a detectable trace, or learns to live within the limits of its solar system. This interpretation is consistent with everything our telescopes have ever observed. We have found no Dyson spheres, no megastructures harvesting the energy of distant stars, no obvious technological signatures, no probes drifting through our solar system carrying messages from elsewhere. The galaxy, as far as we can tell, looks exactly like a galaxy where intelligent life arises repeatedly and is then confined to its origin point. It does not look like a galaxy where someone has already escaped the box and started spreading through the void. If anyone had escaped, we would see the evidence. The evidence is not there. Some researchers have run the numbers in considerable detail. Anders Sandberg, Eric Drexler, and Toby Ord at Oxford published a paper in 2018 examining the Fermi paradox using updated estimates for the parameters of the Drake equation, the famous formula that attempts to estimate the number of communicative civilizations in our galaxy. Their analysis suggests that under reasonable assumptions, there is a substantial probability that we are the only technological civilization in the Milky Way. Not because life is impossible elsewhere, but because the combination of factors required for a civilization to arise, survive long enough to develop technology, and then succeed in colonizing the galaxy is so improbable that it may have happened exactly once in our galaxy's history. We are the lonely outcome of an extraordinary sequence of contingent events, and we are constrained by the same physics that would constrain anyone else in our position. Now consider what this means for the commitment required to even attempt an interstellar mission. Suppose, for the sake of argument, that some future version of human civilization decides to try. They have somehow solved propulsion. They have built the shielding. They have selected and trained a crew. They have assembled the spacecraft. The launch is imminent. The cost of this mission, by any reasonable estimate, would dwarf the entire budget of any nation that has ever existed. The spacecraft itself would be a city-sized vessel constructed in orbit over decades. The propulsion infrastructure would consume the raw materials and industrial capacity of multiple planetary economies. The fuel, if it is antimatter, would require dedicated production facilities operating for centuries. If it is fusion fuel, it would require vast deuterium and helium-3 mining operations across the solar system. The energy investment is staggering. And here is the fifth dimension of the problem. The civilization that begins building such a ship might not be the civilization that finishes it. The construction time alone could span multiple human generations. The political systems that authorize the project must remain stable across that span. The economic systems that fund it must continue to allocate resources without interruption. The scientific institutions that designed it must maintain their expertise across changes in personnel, leadership, and priorities. Any failure of continuity, any war, any revolution, any economic depression, any shift in cultural values can derail the project before it ever launches. History is littered with grand civilizational ambitions that foundered on the rocks of changing circumstances. The pyramids of Egypt were built across multiple pharaonic generations only because the institutional structure supporting them remained stable for centuries. Most large engineering projects in human history have been completed within a single generation. The few that span longer have required either rigid theocratic or monarchic continuity or astonishingly persistent democratic consensus. An interstellar mission requires consensus across centuries. It requires the conviction that the descendants of today's decision-makers, Descendants who will never meet the people who launched the project and may live in a society radically different from ours will continue to support the goals their ancestors set. This is asking for a kind of long-term commitment that human civilization has rarely demonstrated. We struggle to maintain commitments to projects with payoffs decades in the future. Climate change, infrastructure investment, debt repayment, all of these have proven extraordinarily difficult to sustain across the relatively short time horizons of modern political cycles. A project requiring committed support across centuries faces obstacles that go beyond technology. They are obstacles built into the structure of human social organization itself. There is also the question of motivation. Why would any civilization undertake such a project? The traditional answers are exploration, science, expansion, survival. But each of these motivations weakens under careful examination. Exploration for its own sake might motivate small groups of enthusiasts, but is unlikely to sustain civilization-level investment for centuries. Scientific knowledge can be acquired far more cheaply by sending robotic probes or by building larger telescopes. The science return per dollar of an interstellar mission is among the worst of any scientific investment imaginable. Expansion makes sense if your civilization is running out of resources or space, but the solar system contains far more resources than humanity could ever exhaust, distributed across worlds and asteroids that are vastly easier to reach than another star. Survival, the argument that humanity should spread to other star systems to ensure the species continues even if Earth is destroyed, sounds compelling but breaks down under examination. The threats that could destroy Earth, asteroid impacts, supervolcanic eruptions, runaway climate change, nuclear war, are far more cheaply mitigated by investment in Earth-based defenses than by interstellar colonization. A self-sustaining colony in the asteroid belt, or on Mars, or in the outer solar system would provide effectively the same survival insurance as a colony at Alpha Centauri, at a fraction of the cost. So the question becomes whether any civilization would actually choose to make this investment. The economic argument is weak. The scientific argument is weak. The survival argument is weak. What remains is something closer to religion or art. The act of attempting an interstellar mission becomes a statement about the values of the civilization undertaking it, an expression of its character rather than a calculated investment toward concrete returns. Civilizations have certainly undertaken such projects in the past. The great cathedrals, the moon landing, the construction of major scientific instruments. But these were all efforts measured in years or decades, not centuries. And they were all undertaken by civilizations that were clearly thriving, with abundant resources and stable institutions. Whether any civilization can sustain a multi-century commitment to a project whose payoff arrives long after every original participant has died remains genuinely uncertain. This is one reason some thinkers have proposed that the Great Filter might not be a single technological obstacle, but a sociological one. Civilizations might routinely develop the capability to launch interstellar missions, only to never actually launch them because the necessary commitment proves impossible to sustain. The technology exists, in some sense, but no one ever builds the spacecraft. The species turns inward, develops virtual realities, focuses on local concerns, and gradually loses the imagination required to attempt the crossing. The galaxy fills with civilizations that could go to the stars but never quite get around to doing so. From outside, the result is indistinguishable from a galaxy where the technology never existed at all. But let us assume, against all these obstacles, that a civilization does attempt the crossing. They build the spacecraft, they launch it. They send their best minds across the void. What happens next? The first decade of the journey is the easy part, comparatively. The spacecraft is fresh from construction. All systems are operating at peak efficiency. The crew is healthy and motivated. They are still in radio contact with Earth, with delays of hours rather than years. They are still close enough to home that the psychological reality of permanent exile has not fully sunk in. They watch Earth recede in the rearview cameras, dwindling from a blue dot to a pinprick to nothing distinguishable from any other star. They monitor their systems. They run their experiments. They prepare for the long haul ahead. Years pass. The spacecraft accelerates through the outer reaches of the solar system. Crew members settle into routines. Personal relationships form and break and reform. Children are born if the mission plans for it. The crew learns the texture of confinement. the strange feeling of inhabiting a closed environment that they will never leave. The ship becomes their entire world. They no longer think of themselves as visitors. They have become inhabitants of a new kind of existence, something between a community and a single organism, bound together by walls of steel and the absolute certainty that they cannot leave. Decades pass. The communication delays grow severe. Messages from Earth begin arriving years after they were sent. The crew receives news of events that occurred when they were younger, news that is meaningless because the people who would have cared about it back home have moved on to new concerns. They start to lose touch with the cultural reality of their home planet. The references that mattered to them at launch have faded into history. The political systems they knew have changed. The scientific consensus they were trained on has been superseded. They find themselves becoming time travelers, gradually. By simple persistence in their motion forward through space, components begin to fail. This is the first major test of the spacecraft's design. Even the most reliable systems have lifespans, and a vessel intended to operate for decades or centuries will inevitably accumulate failures over time. Most failures will be minor. A sensor stops reporting. A pump shows reduced efficiency. A computer module needs replacement. Each one is fixable, in principle. The crew has spare parts. They have manufacturing capability. They can build replacements from raw materials. But each failure consumes resources. Each fix degrades the redundancy of the systems. Slowly, almost imperceptibly, the spacecraft loses the margin between functional and broken. The crew lives in growing awareness that they are running on systems originally built for them by people who are now decades dead, and that no replacements will ever be sent from home. The biggest failures, when they come, are catastrophic. A major reactor problem, a breach in the hull, a failure in the life support recycling that suddenly makes the air poisonous over the course of hours. The crew responds with whatever skill and ingenuity they can muster. Some failures kill people. The mission has medical facilities, but they are limited. Surgery without specialists, treatment without backup, decisions made by individuals who must accept that they cannot consult anyone qualified to second-guess them. The crew shrinks over time. Funerals are held. Bodies are processed by recycling systems that turn human remains into nutrients for the hydroponic gardens. The ship becomes a closed loop, and that loop includes its own dead. There is something deeply uncomfortable about contemplating this, but it is the inescapable reality of any closed system long-duration mission. Every atom of carbon and nitrogen that the crew uses must be reclaimed. Nothing can be wasted. The psychological effects of this kind of existence are difficult to predict because no human society has ever experienced anything like it. The closest analogs are isolated indigenous populations on remote islands. But even those communities had vastly more space and more contact with the natural world than any spacecraft could provide. The crew of an interstellar mission lives inside a metal box drifting through nothing. They see the stars through cameras and viewports, but those stars are unreachable, unchanging, impossible to interact with. The void outside is not empty in any meaningful sense, but neither is it full of anything they can engage with. It is a backdrop, an unchanging panorama against which their tiny, self-contained world floats forward through years that mean nothing to anyone but them. Religion, art, and politics evolve aboard the ship. They have to. A community of humans cannot maintain itself without these structures. But the structures aboard a spacecraft will not be the same as the ones at home. New traditions emerge. New languages develop. The original mission objectives, written down in detail by the people who launched the ship, become subject to interpretation by descendants who have never known any other life. Some descendants accept the mission. Some come to question it. Why are we doing this, they ask. Who decided that we should spend our entire lives flying toward a star we will never reach? The original crew chose this fate. We did not. We were born into it. Generation ships face the question of intergenerational consent in a particularly stark form. Every child born aboard such a vessel is born into a fate they did not choose, with no possibility of escape. Some philosophers have argued that this is a fundamental moral problem that may make generation ship missions impossible to justify ethically. You cannot ask the unborn whether they consent to spending their entire lives confined to a spacecraft. They have no choice in the matter. They will live and die aboard the ship because their parents and grandparents made that decision generations earlier. Whether this is meaningfully different from any other situation in which children inherit the consequences of their parents' choices is a question philosophers have debated extensively. But the extreme nature of the constraint, the absolute impossibility of changing your mind once you are aboard, makes it qualitatively different from ordinary inheritance. There is also the question of what happens to the mission's purpose if subsequent generations decide they do not want to complete it. Suppose the great-great-grandchildren of the original crew, having lived their entire lives aboard the ship, decide that the destination star is irrelevant to them. They have made the spacecraft their home. They do not see why they should arrive somewhere new and start over when their current life is satisfactory. They alter the spacecraft's trajectory, putting it into a stable orbit somewhere in interstellar space. They simply continue living as they have been living. The original mission is abandoned. The investment of the launching civilization is lost. The crew has effectively become a new species, no longer connected to the goals or values of their ancestors. This scenario is not implausible. It is what would naturally happen if generations of humans were placed in a confined environment with no way to verify the original mission's importance. The mission becomes mythological. Its purposes become abstract. The actual people aboard the ship have to decide for themselves whether to continue, and there is no one alive who can persuasively argue that the mission still matters in the way it did to the people who launched it. The destination, when it is reached at all, often turns out to be ambiguous. Suppose the spacecraft arrives at Proxima Centauri. The system contains at least one confirmed planet, Proxima Centauri b, which orbits within the habitable zone of its red dwarf star. From a distance, it looked like a candidate for human colonization. Up close, the situation is far more complex. The planet is tidally locked to its star, meaning one face is in permanent daylight and the other in permanent darkness. The day side is too hot for liquid water. The night side is frozen. The narrow ring around the terminator, where temperatures are moderate, is bombarded by stellar flares from the active red dwarf, flares hundreds of times more intense than anything our sun produces. The atmosphere, if there is one, would have been stripped away long ago by the constant onslaught of charged particles from the star. The surface, if reachable at all, is a sterile rock. There is no biosphere to support the colonists. There is no atmosphere to breathe. There is no soil to grow crops in. The colonists would need to construct everything they need from raw materials, sealed inside artificial habitats, never able to step outside without protective gear that protects them from radiation that would kill them within hours. The colonists realize, perhaps slowly, that they have not actually arrived anywhere worth arriving at. The planet they spent decades or centuries traveling to reach is barely habitable, in the most generous interpretation, and almost certainly worse than the spacecraft they are leaving. Some of them choose to remain aboard the ship, continuing the closed system existence they have always known. Others descend to the surface, attempting to build a foothold on a world that does not want them. The colony struggles. Some colonists die. Some return to the ship. The mission, in the strict sense of the word, has succeeded. They have arrived. They have made contact with another star system. But the success is hollow. They have not found another Earth. They have found another harsh alien environment that requires constant artificial support to inhabit, and they have spent generations of effort to reach a place that turns out to be barely better than the void they crossed. This pattern, the discovery that destination worlds are harder to inhabit than the optimistic assessment suggested, may be common across interstellar exploration. Most planets in the galaxy are not Earth-like. Most habitable zones contain worlds that are habitable only in the most technical sense, capable of supporting liquid water under specific conditions, but lacking the rich biosphere and benign environment that make Earth so unusual. The closer we look at exoplanets with our improving telescopes, the more we realize that Earth is a rare and possibly unique world. Most of the worlds we might travel to will resemble it only superficially. The act of colonization will be far harder than the optimists hoped. This realization adds yet another wall to the list: the destination wall. The recognition that even successful interstellar journeys may not arrive at places worth arriving at. The galaxy is full of stars and full of planets, but it is not full of Earths. It may contain very few Earths, it may contain only one, and the one it contains is the one we already inhabit. The places we could travel to are almost all worse than home, in every meaningful sense. The cost of the journey, even if the journey succeeds, may exceed the value of what is found at the other end. Consider what this means for the rationality of attempting interstellar missions at all. Even if the technical challenges could be overcome, even if the temporal isolation could be accepted, even if the psychological burden could be managed, the destinations available are mostly disappointing. Spending centuries of civilizational effort to reach a planet where humans cannot survive without artificial support is not obviously better than spending those centuries developing better artificial support on Earth or in the asteroid belt, or somewhere within the solar system that is far easier to reach. The economics of interstellar travel become questionable when the destinations are evaluated honestly. We are imagining colonies on barely habitable worlds, supported by infrastructure that has to be carried across light years, when we could instead build effectively the same colonies in our own backyard for vastly less effort. This brings us to a strange and disquieting conclusion. The combination of all the walls we have discussed, propulsion physics, radiation hazards, temporal isolation, biological constraints, communication delays, civilizational commitment, ethical problems with generation ships, and the disappointing reality of most exoplanets, leads to a picture in which interstellar travel is not merely difficult, but probably irrational. A civilization that examines the actual costs and benefits would conclude that the rational course is to remain within its home star system, to develop the resources and territories that are reachable, to build the kind of long-term sustainable civilization that does not require crossing impossible distances. The stars are not where the value is. The stars are far away, and getting there destroys you, and the places you arrive at are almost all worse than where you started. This may explain the silence of the galaxy more thoroughly than any single one of the walls considered alone. Perhaps every intelligent species reaches this conclusion. Perhaps every civilization, after enough careful analysis, decides not to attempt interstellar colonization, not because they cannot, in some absolute physical sense, but because they should not. The rational path is to stay home. The rational path is to develop your own star system. The rational path is to live within the constraints the universe imposes on biological intelligence, and not waste resources on crossings that bring nothing but suffering and disappointment. If this is right, then humanity will reach the same conclusion eventually. We will try, perhaps. We will build experimental probes. We will send small missions. We will gather data. And then, after enough time has passed, we will accept what every civilization before us must have accepted. The stars are visible but not visitable. The galaxy is observable but not occupiable. We are confined to our own system, not by inability but by the cold mathematics of cost versus benefit. The rest of the universe will remain forever beyond our reach, not because the universe forbids us from going, but because going makes no sense. We will look outward, dreaming of the stars, and we will stay home. There is one more consideration that deserves examination before we move further. We have been discussing the walls primarily from a physics and engineering perspective, but we have not yet addressed the question of why our solar system itself is structured in ways that make leaving it especially difficult. The configuration of our cosmic neighborhood appears, in retrospect, almost designed to discourage interstellar travel. Other star systems might be easier to leave. Ours is not. Consider the structure of our heliosphere. The bubble of solar wind that protects the inner solar system extends to roughly 120 astronomical units, where it meets the interstellar medium at the heliopause. Beyond this boundary, the protective magnetic field of the Sun no longer shields anything. Cosmic ray intensities double. The interstellar medium begins to interact directly with whatever passes through. Voyager 1 and 2 have crossed this boundary, and their measurements have confirmed that the environment outside is fundamentally more hostile than the environment inside. Any spacecraft attempting to leave the solar system must cross this region. There is no shortcut. The heliosphere ends where it ends, and beyond that point, the gentler radiation environment of the inner system gives way to the harsh galactic baseline. But the heliosphere is not the real edge. The real edge is the Oort cloud, extending out to 100,000 astronomical units. This is where the Sun's gravitational influence finally fades. And the Oort cloud is not empty. It contains trillions of icy bodies, scattered through a sphere so vast that the average distance between any two bodies is enormous, but a sufficiently fast spacecraft passing through such a region would still face some statistical chance of collision. We do not know how serious this risk actually is, because we have never sent a spacecraft through the Oort cloud at relativistic velocities. The Voyagers will eventually pass through it, but they are moving slowly enough that any collision would be merely a slow tap rather than a catastrophic impact. A relativistic spacecraft would face a different calculation, with collision risks that have to be carefully evaluated against the known density of objects in the cloud. And our solar system is moving through the local interstellar medium. This means that the Sun, and everything orbiting it, is plowing through interstellar gas and dust at roughly 23 kilometers per second. From the perspective of an outside observer, our solar system has a wake, a trail of disturbed plasma stretching behind it as we move through the galaxy. From the perspective of someone trying to leave the solar system in the direction we are moving, the situation is even worse, because they have to fight not just the static interstellar medium, but also the headwind created by our motion through it. Interstellar dust grains hit a forward-moving spacecraft with extra kinetic energy due to the relative motion of the solar system itself. The solar system is hurtling through the galaxy, and any spacecraft trying to escape must contend with the consequences of that motion. There is also the gravitational geometry of the local stellar neighborhood. Our nearest stellar neighbors are not arranged in any particularly convenient pattern. The Alpha Centauri system, with its 3 stars, is the closest at 4.24 light-years. But Alpha Centauri itself is a complicated triple system. The 2 main stars, Alpha Centauri A and Alpha Centauri B, orbit each other on an elliptical path that takes them between 11 and 36 astronomical units apart. This complex orbital dance creates a region of gravitational instability between them, where stable planetary orbits are difficult to maintain. Proxima Centauri, the 3rd member of the system, orbits the inner pair at a great distance and is itself a flare-prone red dwarf with a single confirmed planet that suffers from tidal locking and stellar radiation. The other nearby stars, Barnard's star, Wolf 359, Lalande 21185, are mostly red dwarfs with similar problems. The stars within 20 light-years of us include very few that resemble our Sun in size, age, and stability. The few that do, like Tau Ceti at 12 light-years and Epsilon Eridani at 10.5 light-years, may host planets but face other complications, such as Epsilon Eridani's young age and active dust disk that may make the system a dangerous place for incoming spacecraft. This means that even if we wanted to attempt a journey to the most plausibly habitable nearby star, we are choosing among a small handful of options, none of which is unambiguously promising. Our solar system happens to be located in a region of the galaxy where the nearest neighbors are not particularly inviting. Civilizations elsewhere in the galaxy might find themselves in clusters of sun-like stars with stable, long-lived companions, where interstellar journeys could be measured in light-years rather than tens of light-years. We do not have that luxury. We are isolated, gravitationally surrounded by mostly red dwarfs and complex multi-star systems. The structure of our cosmic neighborhood adds another layer of difficulty to an already impossible task. Consider also the position of our Sun within the galaxy. The Milky Way contains zones where star formation is intense, where supernovae erupt frequently, where the radiation environment is too hostile for stable planetary biospheres to develop. There are also outer regions where stars are too sparse and metal-poor to produce rocky planets at all. Between these extremes lies what astronomers call the galactic habitable zone, a band of the galaxy where conditions are favorable for life. Our Sun sits comfortably within this zone, neither too close to the chaotic galactic center nor too far out in the metal-deficient suburbs. This is part of why life arose here, but the same favorable position that protects us from the worst of the galaxy also limits our access to it. The galactic habitable zone is broad in some dimensions but narrow in others. Stars within easy reach of our Sun, geographically speaking, are largely the same kinds of stars our Sun is near, with similar properties and similar limitations. Reaching dramatically different environments, regions where stars are younger, denser, more massive, requires longer journeys through more hostile space. The kinds of star systems that might be most scientifically interesting to visit are also the kinds that are hardest to reach safely. There is a quiet horror in recognizing all of this. Not the loud horror of impending catastrophe, but the slow, settled horror of realizing that the dream so many people have carried since childhood, the dream of humanity spreading across the galaxy like the sailing vessels once spread across the oceans, may simply be impossible. Not a matter of waiting for better technology, not a matter of summoning sufficient willpower, not a matter of finding the right inspiration or the right leadership or the right historical moment, just impossible, in the way that traveling backward in time is impossible. A dream that cannot become real because the universe is not built to accommodate it. People sometimes resist this conclusion by pointing to the history of human achievement. Other things were once thought impossible, they say. Heavier than air flight, reaching the moon, splitting the atom, sequencing the genome. We were told these things could not be done, and we did them anyway. Why should interstellar travel be different? Why should this challenge defeat us when so many others have not? The answer is that the challenges that have been overcome were always engineering challenges, not physical limits. Heavier than air flight required clever design, but birds had been flying for hundreds of millions of years. Reaching the moon required enormous resources, but the moon was reachable in principle, and the physics was straightforward. Splitting the atom required deep understanding, but atoms can be split, and the energy released does what physics says it should do. Each of these accomplishments was a question of whether humans could figure out how to do something the universe permits. Interstellar travel is different. The universe does not permit it in any practical sense. The walls are not made of human ignorance. They're made of the fundamental structure of space-time, the fundamental properties of matter and energy, the fundamental geometry of the cosmos. These are not obstacles that yield to cleverness. They are the rules of the game itself. Some optimists hold out hope that future physics will reveal loopholes we cannot currently see. Perhaps the speed of light is not absolute under conditions we have not yet discovered. Perhaps quantum mechanics permits forms of communication or transportation that bypass relativistic constraints. Perhaps dark energy or dark matter contains some property that could be exploited for propulsion. These hopes are genuine, but they should be examined carefully. The history of physics is one of progressive refinement, not radical revision. Newton's laws were not overturned by Einstein. They were extended into a more general framework. Einstein's theory has not been overturned by quantum mechanics. The two have remained in productive tension, each governing different domains, with both passing every experimental test thrown at them. The speed of light has been measured with extraordinary precision. The conservation of energy has been confirmed in every imaginable context. The mass energy equivalence has been verified countless times. The structure of relativity is among the most thoroughly tested theories in the history of science. It is not likely to dissolve into a different framework that suddenly permits faster-than-light travel. This does not mean future physics will offer nothing new. It almost certainly will. There are deep unsolved problems in physics, particularly around the unification of quantum mechanics and gravity, the nature of dark matter and dark energy, the conditions inside black holes, and at the moment of the Big Bang. Solving these problems may produce technologies we cannot currently imagine. But there is no clear path from our current understanding to faster-than-light travel. The mathematics that would permit such a thing requires properties of the universe, like negative energy density, that do not appear in any natural process we have ever observed. The speculations are interesting but not promising. They are not where the smart money is. So we must take the walls seriously. We must consider what it means to be a species confined to a single star system, regardless of how much we might wish otherwise. And the meaning, when examined honestly, is not entirely terrible. It is sobering, certainly. It deflates certain dreams that have animated science fiction and popular imagination for over a century. But it also focuses attention on what is actually achievable. The solar system is enormous. We have explored only a tiny fraction of it. The asteroid belt contains material wealth far exceeding anything available on Earth's surface, with metals and minerals that could support a civilization vastly larger than our current one. The moons of Jupiter and Saturn host environments that, while harsh by our standards, contain the raw materials for habitation and possibly even subsurface oceans where life might already exist. Mars, despite its limitations, could be terraformed over centuries into something resembling Earth. The Sun itself produces more energy in a single second than humanity has used in its entire history. If we learn to harvest even a small fraction of this output, we could power civilizations of unimaginable scale and complexity. The boundaries of the solar system, marked by the Oort cloud, contain enough material to keep us busy for millions of years. A future humanity that accepts the impossibility of interstellar travel and turns its attention to its own solar system is not a defeated species. It is a species that has come to terms with its actual circumstances and is making the most of them. Such a civilization could grow vast and prosperous within the gravitational territory of our Sun. It could produce wonders. It could explore inner questions about consciousness, mathematics, art, philosophy, while also extending its physical presence across the planets and moons and asteroids that orbit alongside us. The stars would remain visible but unreachable, beautiful in the way that distant mountains are beautiful, decorating our sky without being destinations. This vision contradicts the narrative most science fiction has been telling for generations, the narrative in which humanity inevitably spreads across the galaxy, encounters alien civilizations, fights wars among the stars, becomes a galactic species. That narrative may simply be wrong. It may be a fantasy we have invented to comfort ourselves about the smallness of our actual situation. The real future, the future we will actually inhabit, may be one in which humanity remains confined to its home star system, growing in sophistication and diversity within those bounds, but never extending beyond them. The stars in the sky tonight may be the same stars our descendants are looking at 10,000 years from now, in roughly the same configurations, with roughly the same brightnesses, marking the same eternal limit of where we cannot go. There is something to be said for accepting this reality and finding meaning within it. The walls do not eliminate the possibility of a flourishing civilization. They simply define the territory within which that flourishing must occur. Earth itself is a small place compared to the universe, but humans have built rich and meaningful lives on this small place for hundreds of thousands of years. A solar system is enormously larger than a planet, with room enough for civilizations whose scale would dwarf anything Earth has ever contained. Confinement to a single solar system is not the same as confinement to a small box. It is confinement to a very large region of space, large enough to contain dreams that we have not yet begun to dream. But there is also something to mourn. The dream of crossing to other stars, of meeting beings from other worlds, of carrying human consciousness to places where it has never been. That dream has shaped a great deal of human thought over the past century. Letting go of it requires accepting a different kind of universe than the one we have been imagining. A universe in which intelligent species are scattered across vast distances, each confined to its own star system, each looking outward at the others with the same wistful longing, each unable to bridge the gap. A universe of cosmic loneliness, in which the silence of the galaxy is not the silence of emptiness, but the silence of countless trapped civilizations, all waiting for something that will never come. The sky is full of life, perhaps, but the walls between it cannot be breached. If we ever do receive a signal from another civilization, that signal will travel at the speed of light, taking years or centuries to reach us. We can listen, we can possibly respond, but we cannot visit, we cannot meet. We cannot ever shake the hand of an alien being or walk on a world orbiting another sun. The gap is too wide, the walls are too high. We can wave across the void to other intelligences, but the wave itself will take longer than a human lifetime to be returned. Communication with the rest of the galaxy, if it happens at all, will be communication conducted across spans of time that strip every interaction of the spontaneity and intimacy that make ordinary conversation meaningful. We will never know our cosmic neighbors as friends. We may know them as distant correspondents, exchanging letters across centuries, with each letter informing the recipient about a world that no longer exists by the time the letter arrives. This is the universe physics has built. Not a hostile universe, not a malicious one. Just one with rules that happen to make biological civilization fundamentally local. Each civilization is born into its own star system, lives its life within that system, and dies within those bounds. The light from civilizations that lived long ago may reach us, evidence of their existence frozen in radiation that has crossed millions of years to find us. We may eventually detect such evidence, technosignatures from extinct intelligences that flourished before our species existed, but we will never communicate with those civilizations because they are gone, and any new civilization arising during our era will be too far away in space and time for meaningful exchange. We are alone in the way that the inhabitants of distant islands were alone before global communication, except that the gulf separating us cannot be crossed by any technology consistent with the laws of physics. So when you look up at the night sky tonight and see the stars scattered across the darkness, understand what you are seeing. Each of those points of light is a sun, possibly with planets, possibly with life, possibly with intelligence. They are not destinations waiting for humanity to arrive. They are not future colonies of an expanding civilization. They are the unreachable walls of our cosmic prison, decorated with light from places we will never visit, glowing with the warmth of other worlds where our descendants will never set foot. The vastness you see is real, but it is also forbidden. It is exhibition space, not living space. It is something to be observed, theorized about, photographed by telescopes, but not entered. There is a strange peace in accepting this. The frustration of dreaming about something impossible is replaced by a clearer focus on what is actually possible. The solar system becomes infinitely more interesting when you realize it is the only world humanity will ever inhabit. Every asteroid becomes potentially valuable. Every moon becomes potentially habitable. Every gram of material drifting through the orbit of the planets becomes part of the limited resource base that will support all of our future civilization. The wastefulness of our current relationship with our solar system, where we treat the moon as a curiosity and Mars as a far-off destination, and the asteroid belt as a backdrop for science fiction, is revealed as the squandering of irreplaceable territory. If the stars are not available to us, then this is the only space we have. This is the only home we will ever know, and we have barely begun to settle it. A civilization that takes this seriously will look very different from the one we currently are. It will invest in space-based infrastructure with the kind of multi-generational commitment we currently reserve for our most ambitious projects. It will build habitats in orbit, mine the asteroids, terraform the planets, harvest the energy of the sun. It will treat the solar system not as a backdrop for adventure stories, but as the actual territory where the future will be lived. The dream will not be of leaving the solar system, the dream will be of fully inhabiting it. And that dream, unlike the dream of interstellar travel, is achievable. It just requires us to look at the universe as it actually is, rather than as we wish it to be. Some readers of this analysis will object that I have been too pessimistic. They will argue that I have given up too easily, that I have failed to account for the possibility of transformative future technology, that I have applied today's understanding of physics to predict tomorrow's possibilities. Perhaps this is fair. The history of technology is full of examples of impossibilities that turned out to be merely difficulties, of barriers that fell to determined effort, of limits that proved softer than they appeared. It would be hubris to claim certainty that interstellar travel is forever beyond reach. The walls I have described are based on our current best understanding of physics, and that understanding is incomplete. There may be loopholes we have not yet found. There may be principles we have not yet discovered. There may be paths forward that no one currently alive can imagine. But the walls, as they currently exist, are formidable. They are not minor inconveniences. They are not engineering puzzles waiting for clever solutions. They are deep structural features of the universe, deriving from fundamental principles like the speed of light, the conservation of energy, the second law of thermodynamics, the indifference of cosmic radiation to biological life. To overcome them would require not just better technology, but a different physics. And while different physics is possible, in some hypothetical sense, no current line of research suggests that the necessary breakthroughs are imminent or even on the horizon. We are, as far as we can tell, looking at obstacles that would still be obstacles 1,000 years from now or 10,000 years from now, regardless of how much progress we make in other domains. Whatever future humanity becomes, it will likely still face the speed of light. It will still face the rocket equation. It will still face the radiation environment of interstellar space. These are not problems we can outgrow in the way that we have outgrown the problems of subsistence agriculture or pre-modern medicine. They are permanent features of the cosmos, baked into the fabric of how the universe works. If our descendants do attempt interstellar missions, those missions may succeed in the limited sense of placing human-built objects, or perhaps even human descendants, in other star systems. But the success will be limited. The travelers will not return. The information they send back will trickle in over centuries. The civilization that launches the missions will not benefit from them in any practical sense. The benefits will accrue, if at all, to descendants so far removed in time that they may not even share recognizable values with the launchers. Interstellar exploration becomes an investment in a future so distant that no rational economic calculus can justify it. It becomes, instead, an act of pure expression, a statement that the launching civilization wanted to leave traces of itself in the wider universe, regardless of practical benefit. Some civilizations may make this commitment. Most probably will not. And among those that do, the failure rate is likely to be high because of all the walls we have discussed, and others we have not. So when we ask whether humanity will ever leave the solar system, the honest answer is that we probably will not. Not in any meaningful sense. We may send small probes that drift past nearby stars at fractions of the speed of light, gathering whatever data they can during brief flybys, never returning, never establishing any lasting presence. We may send larger missions, perhaps even crude ones, that arrive at destinations after spans of time that disconnect them permanently from the civilization that launched them. We may, in the deepest reaches of speculation, construct generation ships that carry colonies through the void, although the ethical and practical problems with such ships are severe enough that they may never actually be built. But we will not establish a galactic civilization. We will not become a species of the stars. We will remain, fundamentally, a species of one star, our sun, and the system of worlds that orbits it. This is not a conclusion that humanity has yet collectively faced. The stories we tell ourselves still imagine an expansive future, full of colonies on distant worlds, full of spaceships zipping between stars, full of contact with alien civilizations. Those stories may comfort us, but they may also distract us from the harder task of understanding our actual situation. The galaxy is not a frontier waiting to be settled. It is a vast space we can observe but not occupy. Our home is here, in this small bubble around our sun. Our future, however long or short it turns out to be, will unfold within this bubble. The decisions we make about how to organize our society, how to manage our resources, how to relate to the natural world that produced us, all of these decisions matter more than they would if we had the option of walking away to another world. We cannot walk away. There is nowhere to walk to. This is it. This is everything. Maybe that recognition is the most valuable thing such an analysis can offer. Not despair, but clarity. The universe is what it is. The walls are real. The dream of interstellar travel, in the form most popular imagination has carried, is probably not achievable. Accepting this allows us to focus on what we actually can do, which is enormous, even if it falls short of galactic empire. We can build a flourishing solar civilization. We can answer the deepest questions of physics and biology and consciousness within the local resources we already have. We can witness the galaxy through ever-improving telescopes, learning more about it across the centuries, even as we accept that we cannot personally visit any of it. We can communicate, perhaps, with other civilizations, exchanging letters across time, building a kind of distant correspondence that connects intelligent minds across the void without ever bringing them into the same room. There is meaning available within these constraints. There is grandeur within these limits. The universe has not denied us purpose. It has only denied us a particular kind of purpose, the purpose of physical conquest of the stars. Other purposes remain available and may turn out to be more rewarding than the conquest we cannot achieve. But understand the gravity of what is being said. When you look at the night sky tonight, when you see the constellations wheeling overhead, when you spot the bright points that mark the nearest stars, you are looking at a cosmic landscape that humanity will never enter. Not because we lack ambition, not because we lack intelligence, because the universe was built in a particular way, and that way includes barriers that biological intelligence cannot cross. The light from those stars reaches your eyes after journeys of years or decades or centuries. That light is the only ambassador those distant suns will ever send to us, and the only ambassador we will ever send to them. We can wave across the void with our own light. They may wave back if anyone is there, but the waves will take so long to cross the gap between us that the conversation will never be a conversation. It will be a record of past intentions, preserved across time, mailed forward into futures the senders will never see. This is the terrifying reason we may never leave the solar system. Not one reason, but many. Not one wall, but several. Stacked on top of each other, layered through the structure of physics and biology and time, they form a barrier that no civilization, however advanced, can simply punch through. We are inside the box. The box is enormous, far larger than we usually appreciate, encompassing planets and moons and asteroids and a vast spherical cloud of icy bodies extending halfway to the nearest star. But it is a box. The walls are real. And they will still be there in 1,000 years, in 10,000 years, and 1,000,000 years, unchanged by anything we can do. The universe has placed us in a sphere of accessible space and surrounded that sphere with conditions we cannot survive. We can stretch outward to fill the sphere we have been given. We cannot exit it. When you understand this, certain things change about how you see the world. Earth becomes more precious because it is not one home among many, but the only home that ever was. The solar system becomes more important because it is the only territory we will ever have. Other intelligent species, if they exist, become permanent strangers, beings we will never meet, never share a meal with, never collaborate with on any project that could be completed in either of our lifetimes. We are alone in a way that is more profound than we usually admit. Alone in our solar system. Alone in the practical sense, even if there are others scattered across the galaxy, because the others might as well not exist for any purpose that depends on actual contact with them. And yet, alone is not the same as lonely. Alone is not the same as defeated. The solar system contains everything we need to build a civilization of staggering complexity and beauty. It contains energy enough to power us for billions of years, materials enough to construct cities and ships and habitats throughout the planets and moons, time enough to develop into something neither we nor our ancestors could have imagined. The walls keep us in, but they also keep us focused. They define the scope of our project. They tell us where to direct our effort. The stars are off the table. The solar system is on it. And the solar system, properly used, is more than enough. So tonight, when you go outside and look up, take a moment to consider what you are really seeing. The stars are beautiful. They are also unreachable. They are decorations on the ceiling of our world, painted there by the structure of the cosmos, glowing with the warmth of nuclear furnaces that will never warm any human face directly. We can study them with our telescopes. We can imagine them with our minds. We can dream about them in our stories. But we cannot go to them. We were not built to go to them. The universe was not built to allow us to go to them. The walls are too high, the cost too great, the time too long. We are creatures of one star, and that star is the only star we will ever truly know. This may be the deepest secret of cosmic existence. The reason for the silence we hear when we listen for our neighbors. The reason the galaxy looks empty, even though it almost certainly is not. Every civilization is in the same position. Every species is in the same box. The boxes are scattered across an enormous volume of space, each one containing its own intelligent inhabitants, each one isolated from the others by walls that cannot be breached. The galaxy is not empty, it is full of life. But the life is locked in place, distributed across distances that no biology can cross. We are all alone together, each of us in our own private cosmos, each of us looking outward at the other private cosmoses we cannot reach. The terrifying reason we may never leave our solar system is also, in a strange way, the explanation for the loneliness of intelligent life everywhere in the universe. We are not unique in being trapped, we are typical in being trapped. The trap is the default condition of biological intelligence in the universe with these laws of physics. If you find this conclusion unsettling, that is appropriate. It is unsettling. It overturns assumptions that many people hold dear. It deflates dreams that have given direction to centuries of human aspiration. It says, in the end, that the future will be smaller than we hoped. Not smaller in significance, perhaps, but smaller in geographic extent. We will not become a galactic species. We will not encounter alien civilizations face to face. We will not stand on the surface of worlds orbiting other suns. These things are not in our future, regardless of how much we wish they were. The walls will not move. The walls cannot be moved. We have to make our peace with them, or spend the rest of our species' existence beating our heads against barriers that have no door. So make your peace, if you can. The universe is not what you wished it to be. It rarely is, but it is still a universe of immense beauty and complexity, and we still have a place in it, and that place is more than enough for any meaningful life that has yet been lived. The solar system is our home. The stars are our distant companions. The walls are real, and they will remain real. But within those walls, there is room enough for everything we need. There is room enough for everything we are. And maybe, in the long span of time stretching ahead of us, that will turn out to be sufficient. Thank you for joining me tonight on this exploration of the walls that separate us from the stars. If this journey through the deep mathematics of impossibility resonated with you, please take a moment to like the video and subscribe to the channel. It helps deep space signals reach more curious minds, and it allows me to keep producing these long-form examinations of what the universe actually permits and forbids. The next time you look up at the night sky and see the stars, remember what you are really seeing. Not destinations, but boundaries. Not invitations, but reminders. Light from places we will never reach, glowing across distances we cannot cross, painted on the ceiling of the only world we will ever truly inhabit. Sleep well tonight, knowing that home is here, that home has always been here, and that home, against all the reasons it should not be enough, somehow still is. But before we end completely, there is one more thing worth saying. Because the walls we have explored tonight are not just abstract limits in physics textbooks. They are walls that shape every aspect of how intelligent life can exist in this universe. And understanding them does not just tell us about our own situation. It tells us something about what intelligence itself must mean, what it must look like, what it must do, in a cosmos arranged the way ours is arranged. Consider, for a moment, the shape of a civilization that has accepted the walls, that has stopped trying to break them, that has turned its attention inward, toward the territory it actually possesses, and begun to develop that territory with everything it has. Such a civilization would not be small. It might be vast in a way we struggle to imagine, because the resources of even one star system are sufficient to support populations and projects that dwarf anything our planet has ever hosted. The energy output of the sun, harvested with reasonable efficiency, could power trillions of inhabitants living at standards far beyond our current best. The materials of the solar system, properly mined and processed, could construct cities and habitats and ecosystems on scales that make Earth seem cramped. A civilization that fully inhabits its solar system is not a small civilization. It is enormous. It is just enormous in one specific direction, contained within a sphere a few light hours across, rather than scattered across a galaxy. What would such a civilization spend its time on? Not interstellar exploration, because that is closed off. Not conquest, because there is no one nearby to conquer. Not expansion, beyond a certain point, because the system itself defines the maximum extent. Such a civilization would have time, vast amounts of time, to dedicate to the questions that have always animated thinking beings. The nature of consciousness, the structure of mathematics, the properties of art, the relationships between minds, the deeper implications of physical law, the history of life and the universe. These questions are not bounded by physical distance. They expand inward rather than outward. A civilization confined to its solar system might develop philosophical and scientific traditions of unprecedented depth, simply because it has nowhere else to direct its energy. The walls might force a kind of intellectual flowering that civilizations with infinite frontiers never achieve. There is also the project of becoming slowly comfortable with the silence of the galaxy. If our species lasts long enough, we will eventually accept that the silence is permanent. Not because no one is out there, but because the walls separate us from anyone who might be. We will build observatories that listen for techno-signatures from across the galaxy. We will scan the spectra of distant stars, looking for signs of artificial atmospheric chemistry. We will perhaps detect, somewhere across the immense gulf, evidence of another civilization's existence, and we will know that we cannot meet them. We will exchange messages, perhaps across centuries. We will understand intellectually that we are not alone. But the practical consequences of that knowledge will be limited, because action across light years is not really action at all. It is gesture performed across time, more like a prayer than a conversation. Some of our descendants may find this acceptable, others may find it unbearable. The question of whether biological intelligence can sustain itself indefinitely, knowing that it is confined to a single star system in a galaxy full of unreachable peers, is not a question we currently have the answer to. It may turn out that the existential weight of confinement crushes civilizations over long enough timescales. It may turn out that civilizations cope with this weight by retreating into virtual experiences, by simulating the interstellar adventures they cannot actually have. It may turn out that the inability to expand outward redirects energy toward inward growth, producing minds and cultures that would astonish anyone who could see them. We do not know. No civilization that has ever existed on Earth has faced exactly this question, because no civilization on Earth has ever fully recognized the walls. We are perhaps the first generation to begin to see them clearly. Our descendants will be the first to live with the implications. There is one consoling thought worth carrying away from all of this. The walls do not just confine us, they confine everyone. If there are alien civilizations elsewhere in the galaxy, they face exactly the same constraints. They cannot reach us any more than we can reach them. The galaxy is not full of expanding empires that have somehow missed our small corner. It is full, if it is full of anything, of trapped civilizations, each one looking outward at the same unreachable horizon, each one wondering the same things we wonder, each one perhaps comforting itself with the same recognitions we are arriving at now. The universe is not arranged to favor anyone. It applies the same rules to everyone. And under those rules, isolation is the default. We are not uniquely cursed. We are simply experiencing the standard condition of intelligent life in a universe with these particular laws of physics. That recognition is, in its strange way, almost peaceful. We are not failures for not having reached the stars. We are normal. We are doing what every civilization in our position must do, which is to live within the boundaries we have been given, to find meaning where we are, to develop the territory available to us as fully as we can. The shame would be if we knew the walls were there and pretended they were not. The shame would be if we wasted our finite resources on doomed attempts to break through, when we could be building something extraordinary within the space we have. There is no shame in confinement that is universal. There is only the work of making the most of what we are. So when you go outside tonight, when the stars are visible above you, take that long look. Take it knowing what you are seeing. Light, traveling across distances that defy measurement, arriving at your eyes after journeys longer than human history. Each photon a messenger from a furnace that will never warm you, glowing in the cold dark to mark territory we cannot enter. The constellations are old, far older than our species, and they will remain visible long after our species has either thrived or vanished. Our descendants, if we have any, will look up at roughly the same patterns of stars in roughly the same positions, separated from us by time but connected to us by the same unreachable sky. The night sky is permanence. It is the one feature of our existence that does not change on human timescales. It will be there tomorrow. It will be there in 1,000 years. It will be there long after every other thing we have ever built has crumbled into dust and been forgotten. And we will remain here, beneath it, looking up. That is what intelligent life does in this universe when it has accepted its actual situation. It looks up, it wonders, it dreams about the unreachable, and it builds within the reachable. It fills its solar system with cities and stories and discoveries, and it accepts that the rest of the cosmos belongs to other observers in other solar systems doing the same thing. The galaxy is a community of isolated thinkers, each one fully present in its own world, each one waving across the void with light that takes too long to be answered. We are part of that community now, whether or not we ever hear from any of the others. We have joined it just by becoming the kind of beings who can look up and recognize what we are looking at. The walls are real. The terror is real. The disappointment is real. And so is the strange dignity of accepting all of it, of standing here on this small planet in this small system on the edge of one minor spiral arm in one ordinary galaxy among trillions, and saying, yes, this is where we are. This is what we have. This is the shape of our existence. And we will live here as fully as we can for as long as we can, because there is nothing else to do and nowhere else to go and no point in pretending otherwise. The stars are not waiting for us. They are not punishing us. They are just there, distant and luminous and forever beyond reach, decorating the only home we will ever know. Thank you, again, for taking this journey through the walls of impossibility with me. If exploring the deepest constraints on what biological civilizations can ever achieve is the kind of thing you find yourself drawn to, please take that small moment to like and subscribe so that deep space signals can keep producing these long examinations of the cosmos and our place inside it. Tonight, when you finally close your eyes and drift towards sleep, hold this thought close. The universe is enormous, almost all of it forbidden to us, almost all of it locked behind walls we cannot cross. But the small portion that belongs to us, the sphere of space surrounding our sun, the planets and moons and asteroids and frozen comets that share our gravitational territory, that small portion is enough. It has always been enough. And it will be enough for as long as we have the wisdom to recognize it. Sleep well, and dream of the home we have, the home we are still discovering, the only home that biology will ever permit us to know.